We've now seen an application that lets you create a KD tree dynamically by adding points based on user input. Another application of this KD tree structure is to find, in a collection of points, which one is closest to a particular query point. And this is something that requires a little bit of attention to detail. We can already use the KD tree to find a particular point that's in the tree that's just a lookup. But how do I find the point that's closest to another point which is already not in the tree? That's exactly the problem. So we're going to use an algorithm called the nearest neighbor query. I'm going to show you the pseudocode now, and then I'll be showing you the application that actually demonstrates this code running. And so what we're going to have to do is make some small modifications to the KD tree class itself, and then launch an application that takes advantage of that new capability. The nearest neighbor has the following structure. It makes the following question. Where do I look for the closest point given an arbitrary point x? I guess I could always use a naive approach and just look through all my points, and that would be order n. But I've been trying to find an efficient way of doing so. Shouldn't there be some way of taking advantage of the KD tree structure? Because if you think about looking for a point in the KD tree, I can look above or below and throw away half the points from consideration. The trouble is, the partitioning, while it separates the points up in a nice disparate way, doesn't encode any information about how close 2 points are. And so I have to do a little bit of work. And the algorithm that's been developed takes advantage of the following properties. You're trying to find the closest point to a particular query point x. Go through the motions and try to see where you would actually insert that point x. You're not going to insert it, but go through the motions and say, find the parent node, which is where you would be inserting if you chose to insert. That's a good way to localize your search. And since I know that that's log n behavior, I know it's a rather efficient operation. So I can quickly narrow down to a particular region where this is probably containing the closest point to my query. But you can't be sure, because these regions, while they don't overlap, they have an unusual geometry, so that the closest point to a particular point might not be in that region. It might be in a neighboring region, just to the left or just below. So we have to do a two-step process. And the way I'll describe the algorithm is by saying, we'll start with the first part. Go through the motions and find the parent, where if you actually did insert x, that would be the parent node of this point. Once you have that, you've got a good estimate for what you believe to be the minimum point, the point that's the minimum distance from your query point. But you have to be sure. And in this rather elegant solution, the way that it determines if it's sure is it goes back to the root and it does another traversal. This time, now that it knows a point, which is its best estimate for what is the closest point, it does a traversal as follows. It looks at the node and it says, well, am I closer to that point, which is my best estimate? And if so, that's now my new minimum distance. So you'll notice that this nearest function is always passing along a value called min, which is the current best estimate for the minimum distance. I use that to kickstart the process at the beginning by doing that first step, finding where the target node would have been inserted and using that parent as my best estimate for the min, and then letting the recursion continue, always refining it as I go on. And the way that the recursion works is as follows. If you ever find a point in this recursion that actually is closer to your potential target, then you say, okay, now I found it. And you allow the recursion to proceed, but there's some special cases you have to consider. And the way that I've chosen to sketch it out here in the code is as follows. If you are faced with a point that's partitioning a space into two sides, which side do you go to find the one that's closest to your query point? It may be that it's too close to call. It may be that you have to try both. Now, the good news when it comes to the analysis of this algorithm is that you only find yourself in that situation a rare number of times. So it's not as if every time you go through the recursion, you've got to try to look at both sides. It's only a rare number of times. And that allows me to say with certainty that in the average case, you have log n behavior. At the same time, I know that this data structure is not balanced. I haven't done anything to demonstrate how I could balance a KD tree. And so I could have a KD tree which is really disproportionate in terms of the space of the partitions. And that's why in the worst case, it could still be order n to go through the process. But after all, that's not that bad. Linear time is not that bad. I'm holding out hope for doing a logarithmic performance. And if the decision is not too close to call, then I actually have a very clear signal to tell me whether to go below or above. And based on all the information, I quickly traverse the tree and find the point that I'm interested in that's closest to my target query point. We're going to show you this implementation in code, but to do that, I have to make a change to the KD tree itself that implements this. Instead of doing that line by line, I'll show you the full code, and then we'll explain it in context. I'm now going to show you the changes that I made to the KD tree and KD nodes to support the nearest neighbor query. Some of the coding is a little convoluted, so instead of doing it in an interactive form, I'm just showing you the final product, and I encourage you to look at that and experiment with it on your own. The way that the nearest neighbor query works, as I mentioned, is that you first have to find what node would be the parent if I had actually inserted a particular query point. That can be done through a recursive process, which you've seen when I do the drawing of the partitions in that application just a moment ago. But you can also do it in a non-recursive form, and this is another theme that we've talked about in algorithms, is that you can always take recursive operations and through some implementation tricks, you can turn those into a iterative form without having to call multiple functions. Here, I'm going to traverse the root from self.root and traverse all the way down until I get to the point where I've run out, and that's when I know that that is the location where you would have inserted the point, and what I have left behind is the parent. So this code over here is going to compute a node n, which would be the ultimate parent if I had chosen to go ahead and insert p into the KD tree. Once I have that point, I compute the minimum distance, called min d, and then I go and I ask the root, can you find, is there a node that's closer, by traversing from the root all the way down? And this engages the logic that I mentioned in the PowerPoint slides. As you're traversing from the root back down to that location, it may be that you get to a partition where the decision whether to go above or below is too close to call, and so you have to do both sides. Other times the decision is clear, and you just go down one side or the other. So we need to look at what this nearest function does. This is a function that is here inside the KD node. As you can see, it's a little complicated. The way that it works is by having available this function called the distance, which is a new function that I've added. Distance does nothing more than compute the Euclidean distance between a point and the node so that I can determine how far away it is. The way that nearest works then is by finding out, well, I know what my current min distance is, that's min d. Is it possible that I found a node in this traversal that's actually closer? And if you ever find one that's closer, then that becomes the one that you're going to be passing back. That's your result. And of course, you always have to update the min d to get further and further, closer and closer approximations to what you believe to be the actual closest point. When I want to determine whether I go left or go right, or to go above or go below, the decision is based on, well, how close I am to the points that are present there. And the way that's determined is by means of what's called a perpendicular distance. I don't need the Euclidean distance anymore. I now need to just shoot left or shoot up and down and see how far away I am from that partition. Because it could be that I'm currently, min d is my current estimate for how close I am to the point that I've estimated to be the best one. But it might be that I come to a partition, and even though that min distance point is the one that I believe is the best, I've got another point that's right on the edge of the partition. And the only way to determine that is to go on both sides of the partition. And that's what it does here. It checks the above side and it checks the below side to see if we can find one that's closer. The easier case is shown down here. It may be that I have to check above or check below, and in either one, I just make my decision. What I'm now going to show is an app that takes advantage of this to actually demonstrate that it's working. And to do this, I'm going to introduce a method. Sometimes when you're dealing with points, we forget that when you represent on a screen, that point is just 1 pixel wide. So it becomes very hard to try to move your cursor just over a particular point to use that as a querying device. So what I'm going to do is arbitrarily decide that if I'm within 5 pixels of a particular point, I'm going to call that good enough. And so what this find method does, it is a traversal over the tree to try to see if a particular point is within 5 pixels of one of the nodes in the tree. So let's demonstrate this using an extension of the KDTree app that I just showed you. I call this the final app nearest neighbor. What it's going to do is basically the same thing it did before. It will let me add points, and you'll see the KDTree appear on the screen, the vertical partitioning, then the horizontal, and so on. But there's going to be a slight difference now. Now when I add a point, I'm always keeping track of which point in my set is closest to my current cursor coordinate. Naturally, in a set with just 1 point, that's the only one that you see. And if I move my mouse right over that point, you'll see that it turns red. Again, I'm within 5 pixels of that center point, and that's how I know that I have located that point. So those are the two methods that I'm demonstrating. The first one is the nearest neighbor query that just continually searches to see what's the nearest point and then draws the line in real time. And the other one is a quick determination. If I'm ever within 5 pixels of an actual point, I want to draw that point using red. Well, now I've got 2 points. Where's the closest one? You'll notice over here, the closest point, whether I'm in the top partition or the bottom partition, is this one here. And there's some middle point right along this line that you're exactly halfway between both those 2 points. If I'm on this side, I'm so far away from this point over here that there's no point in checking those points on the right-hand side. And that's why the nearest neighbor can really tremendously cut down the search space if you have a cluster of points, which I'm about to add right now. So if I have these points here, as I'm moving my cursor, you can see that it's rather rapidly, very efficiently, I would say, finding the closest point and doing so in a way that's recursive and takes advantage of the structure of the binary KDTree to throw away half the points from consideration. And yet, I still have these intermediate points here, like you see there or there, that are actually closest to that and reflect that point. And when I get right over one, as you see here, when I'm directly over the node, you see that it turns color to suggest that I found the one I'm looking for. This particular implementation takes advantage of the implementation of the KDTree that I've just made. Both those code files will be available for you to experiment with on your own. This completes the implementation of the KDTree and its corresponding applications.